Hello, my name is Jeremy, and I will be your instructor for this course. As a former naval nuclear engineer, dealing with the hazards of hydrogen sulfide was a daily part of my life. Now I get to share my knowledge and experience with you. By the end of this course, you will be able to identify hydrogen sulfide hazards and the engineering and administrative controls you can use to mitigate that hazard. Operate personal gas monitors correctly, including performing bump tests and responding appropriately to alarms. Establishing and evaluating ventilation controls. Distinguish between confined spaces that allow alternative entry and permit-required confined spaces that require full program. Understand signs that may indicate your controls are ineffective and it is time to leave the space. Execute your stop work authority when hazardous conditions emerge or controls are ineffective. Before we move on to mitigation, let's do a quick review on why hydrogen sulfide is so incredibly hazardous. Hydrogen sulfide, or H2S, is a colorless, extremely toxic gas. It is heavier than air, which means it can collect in low-lying or enclosed spaces. It is commonly encountered in oil and gas operations, wastewater systems, sewers, pits, tanks, and confined spaces. Exposure can overwhelm the body very quickly, leading to collapse or death before a worker has time to react. Smell is not a reliable warning, and dangerous conditions can exist without obvious signs. Because hydrogen sulfide acts quickly and without reliable warning, prevention and control are critical. Monitoring, ventilation, and controls exist to keep conditions safe, not to allow workers to push through hazards. In this module, we will concentrate on detection and monitoring. These are fundamental pillars in hydrogen sulfide hazard mitigation. Hydrogen sulfide cannot be properly managed unless it is detected early, measured accurately, and monitored continuously. Continuous monitoring provides the information we need to determine if we can continue working safely or if we need to stop and exit. Many facilities use fixed hydrogen sulfide detection systems to monitor specific areas, processes, or equipment. These systems are typically installed near known or potential release points, such as process units, tanks, pits, or enclosed spaces. Fixed detection systems are designed to continuously measure hydrogen sulfide concentrations, activate audible and visible alarms, alert workers, control rooms, or centralized monitoring systems. Fixed detectors provide important area-level protection, but they are limited to the locations where they are installed. Hydrogen sulfide concentrations can vary significantly within the same work area, especially in low-lying or enclosed spaces. For this reason, fixed detection systems do not replace personal gas monitors. Personal gas monitors are worn by individual workers and measure the air in your breathing zone. These monitors move with you and provide real-time feedback on changing conditions. Personal monitoring is critical because hydrogen sulfide can accumulate unevenly, can migrate rapidly, and may be present in one location and absent just a few feet away. You must wear your monitor correctly to provide meaningful protection. Place the monitor in your breathing zone, typically on your upper torso, such as a shirt collar, chest pocket, or lapel, close to your nose and mouth. Wearing a monitor on your belt, in a pocket, or inside clothing can delay detection and prevent alarms from activating when hydrogen sulfide reaches your breathing zone. Your monitor must remain powered on, unobstructed, and audible throughout the task. A gas monitor that is not worn correctly may detect hazardous conditions too late or not at all. When worn and used correctly, your personal gas monitor provides early warning and allows you to leave before conditions become dangerous. Gas monitors are essential safety devices, but they have limitations. Monitors may fail or provide inaccurate readings if sensors are damaged, expired, or contaminated, batteries are low or depleted, required bump testing or calibration has not been completed, environmental conditions such as moisture or temperature extremes affect the sensor. Because of these limitations, workers must never assume a monitor is functioning correctly without required checks and verification. Hydrogen sulfide detectors rely on chemical reactions inside the sensor. Certain conditions can interfere with or overwhelm that process. Sensor poisoning occurs when the sensor is exposed to substances that damage or degrade its ability to react properly. Some chemicals can permanently reduce sensor sensitivity, cause the monitor to underread, or fail to alarm. Sensor overload can occur when hydrogen sulfide concentrations are extremely high. At very high levels, the sensor may be saturated and unable to respond accurately. In some cases, readings may lag, lock up, or fail altogether. Gas monitors must be tested before each use to ensure that they will respond correctly when hydrogen sulfide is present. This is called the bump test. A bump test is a functional check, not a calibration. Its purpose is to confirm that the monitor can detect hydrogen sulfide and that the alarms activate as designed. Bump tests are very simple. Expose the detector to a quantity of hydrogen sulfide gas. If it doesn't alarm, do not use it. A successful bump test verifies that the sensor is capable of reacting to hydrogen sulfide, the monitor electronics are functioning, and the alarms can be heard, seen, or felt by the worker. It does not verify measurement accuracy. That is the purpose of calibration. Hydrogen sulfide monitors use chemical sensors that are sensitive to age, dirt, and extreme weather. That is why you must never skip a bump test. Calibration is the process of adjusting a gas monitor so its readings match a known, accurate reference. Over time, sensors can drift and display readings that are higher or lower than the actual gas concentration. Calibration ensures the monitor is measuring hydrogen sulfide accurately and responding at the correct alarm points. Before use, workers must check the calibration sticker or label on the device to confirm that it's been calibrated within the required time frame. A monitor that is out of calibration cannot be trusted. If the calibration is expired or missing, the device must not be used and should be removed from service. Gas monitors are designed to warn workers before OSHA exposure limits are reached, not after. Alarm set points are intentionally set below regulatory limits to provide time to recognize rising hydrogen sulfide levels and exit safely. Under OSHA regulations, the permissible exposure limit for hydrogen sulfide is 20 parts per million for a time-weighted average of 8 hours. A maximum peak of 50 parts per million for only 10 minutes is allowed under very limited conditions. These limits are absolute maximums, not targets. Workers should never plan to work up to these values. Gas monitor alarms are set to activate before exposure reaches OSHA limits so workers can act before conditions become dangerous. An alarm means hydrogen sulfide levels are increasing and controls may no longer be effective. An alarm does not mean investigate. It means stop work and exit immediately. Hydrogen sulfide conditions can change rapidly, sometimes within seconds. Continuous monitoring is critical because hydrogen sulfide can be released suddenly. Gas can migrate or accumulate without warning, and ventilation effectiveness can change during work activities. Monitoring is not a one-time check. It is a continuous decision-making tool used throughout the task. Before you enter an area that requires hydrogen sulfide personal monitoring, make sure to do the following. Check the calibration sticker. Make sure that it has been calibrated within the required time frame. If the calibration is expired or the sticker is missing, you cannot use that monitor. Check the battery. Make sure that it is fully charged and that it can last the duration of your task. Never ignore a low battery warning. Check the alarm set points. Make sure that the alarms are set to the values determined by your employer. Perform a bump test. Move to a clear location away from other monitors, equipment, and ventilation. Expose the sensor to the test gas and make sure that the monitor reacts and the alarm sounds. Verify that the visual, audio, and vibrational alarms are all working. Ensure that the monitor recovers. After the bump test, give it time to return to the baseline value. Attach the monitor correctly. It needs to be placed into your breathing zone to make sure that the air that is monitoring is representative of what you are breathing. You can put it on your shirt pocket, on your lapel, clip it somewhere, as long as it's in the breathing zone. Don't put it on your belt or in your pocket or cover it up in some way. If at any point in this procedure the monitor does not respond correctly, do not use it. Obtain a replacement monitor or notify your supervisor. Your employer is responsible for providing monitoring equipment that is properly calibrated and maintained. It is your responsibility to use it properly to perform the pre-work checks and ensure that it remains functional throughout your task. Now, in this section, we will learn how hydrogen sulfide hazards are managed with the use of engineering and administrative controls. Hydrogen sulfide hazards are managed using the hierarchy of controls, which prioritizes the most reliable methods of protection. For hydrogen sulfide mitigation, this course focuses on engineering controls, administrative controls, and personal protective equipment. These controls are emphasized because they can be planned, verified, and monitored during work activities. Engineering controls reduce exposure through physical or mechanical means. Administrative controls manage exposure by controlling how work is performed. Personal protective equipment provides a final layer of protection when exposure cannot be fully controlled by other means. Engineering controls are physical or mechanical systems designed to prevent hydrogen sulfide exposure by removing the hazard, isolating it, or preventing it from reaching workers. Common engineering controls include substitution of materials that do not produce hydrogen sulfide gas, mechanical ventilation systems, local exhaust ventilation near release points, sealed or closed systems that prevent gas escape, process controls that reduce gas generation, fixed detection and alarm systems, and gas flaring. When designed, installed, and maintained correctly, engineering controls provide consistent protection without relying on individual behavior. In some processes, hydrogen sulfide generation can be reduced through chemical treatment or scavenging systems that neutralize sulfides before they can off-gas. These controls work upstream by limiting the amount of hydrogen sulfide available for release. While chemical treatment does not eliminate all risk, it can significantly reduce the severity and frequency of exposure events when properly selected, applied, and maintained. Venting and purging systems are used to safely remove hydrogen sulfide from vessels, piping, or equipment before work begins. These systems are distinct from general ventilation and are intended to clear internal spaces where gas may be trapped or concentrated. Proper venting and purging reduce the likelihood of unexpected releases when systems are opened or disturbed and must be performed according to established procedures. The materials used in equipment and piping can influence hydrogen sulfide generation, corrosion, and release. Certain materials are more resistant to degradation caused by hydrogen sulfide and help prevent leaks, failures, and secondary hazards. Selecting appropriate materials of construction is an engineering control that will reduce long-term risk and support system integrity. Worksite layout and process design can reduce hydrogen sulfide exposure by limiting areas where gas can accumulate and by directing potential releases away from workers. Design features such as elevated release points, controlled drainage, and segregation of hazardous processes help prevent hydrogen sulfide from migrating into work areas. These controls reduce reliance on individual behavior and provide continuous protection. Administrative controls manage exposure by controlling how work is performed and by reducing the likelihood that hydrogen sulfide will be released or encountered. These controls include written procedures and permits that control how systems are opened, isolated, drained, or worked on, cleaning and maintenance schedules that prevent the buildup of organic material, sludge, or stagnant liquids that can generate hydrogen sulfide, restricted access to hazardous areas, required monitoring and verification steps, stop work authority that allows workers to halt work and exit as needed. Administrative controls rely on people following procedures correctly. Because of this, they are less reliable than engineering controls and must be supported by training, oversight, and verification. Wind direction significantly affects how hydrogen sulfide disperses in open or partially enclosed areas. Administrative controls may require workers to approach areas from the upwind side and remain aware of changing wind conditions. Wind awareness helps prevent exposure pathways that engineering controls alone may not fully address. Work in hydrogen sulfide environments may require the use of a buddy system. Having another trained worker nearby increases the likelihood that exposure events are recognized quickly and that assistance can be provided without delay. Administrative controls may prohibit working alone in areas where hydrogen sulfide exposure is possible, especially when conditions can escalate rapidly. Administrative controls are used to limit the number of people exposed to hydrogen sulfide hazards. Reducing the number of exposed individuals lowers overall risk and simplifies emergency response if conditions deteriorate. Certain tasks, such as opening systems, draining equipment, or performing maintenance, have a higher potential to release hydrogen sulfide. Administrative controls may require notifying supervisory personnel before these tasks begin. This ensures that appropriate controls, monitoring, and emergency preparations are in place before work proceeds. When work has the potential to expose workers to elevated or immediately dangerous concentrations of hydrogen sulfide, administrative controls may ensure emergency response readiness. This may include designated standby personnel, clear communication methods, and predefined response procedures. These measures reduce response time and help prevent secondary victims during an emergency. Personal protective equipment is the last line of defense against hydrogen sulfide exposure. PPE does not eliminate the hazard or reduce hydrogen sulfide concentrations. Instead, it places a barrier between the worker and the hazard. Depending on the task and exposure potential, PPE may include respiratory protection, eye and face protection, protective clothing. Because PPE effectiveness depends on proper selection, fit, use, and maintenance, it is less reliable than engineering or administrative controls. In hydrogen sulfide work, the need for PPE, especially respiratory protection, is often an indicator that engineering controls are no longer adequately controlling the hazard. When exposure must be managed at the worker location instead of the source, it signals that higher-level controls have reached their limits or have failed. Personal protective equipment should never be used as the sole means of protection when higher-level controls can be implemented. Detailed respiratory protection requirements are addressed later in this course. While this course focuses on engineering, administrative, and PPE controls, the most effective way to manage hydrogen sulfide risk is to eliminate the hazard whenever feasible. Eliminating the hazard means removing the source or condition that allows hydrogen sulfide to be generated or released. When the hazard is eliminated, exposure controls are no longer required because the risk no longer exists. Even when elimination is not fully achievable, reducing the source can significantly lower reliance on ventilation, procedures, and personal protective equipment. When hydrogen sulfide exposure controls appear complex, fragile, or heavily dependent on personal protective equipment, it is a signal to reassess whether the hazard itself can be reduced or eliminated upstream. Engineering and administrative controls are not permanent solutions. Controls must be reevaluated whenever work scope changes, equipment or processes change, monitoring shows rising hydrogen sulfide levels, ventilation performance changes, an alarm activates or a near miss occurs. Reevaluation ensures that controls remain effective and appropriate for current conditions. If controls cannot maintain safe conditions, work must stop until additional protections are implemented. Ventilation is commonly used to manage hydrogen sulfide hazards. It must be properly designed, set up, and verified to be effective. If ventilation is not effective or the conditions change, the hazards can rise rapidly. The goal of this section is to explain how ventilation works, how to apply it correctly, how to verify its effectiveness, and understand when ventilation alone is not effective. Ventilation is used to dilute hydrogen sulfide concentrations, remove contaminated air from the space, reduce the likelihood that gas will accumulate in your breathing zone. Ventilation is an engineering control. When properly applied and continuously verified, it can significantly reduce exposure risk. However, ventilation only works when it is operating as intended. Natural ventilation relies on open doors, hatches, or openings to allow air movement. It is unpredictable, dependent on wind and temperature differences, and easily disrupted. Because of these limitations, natural ventilation cannot be relied on as the primary control method for hydrogen sulfide hazards. Mechanical ventilation uses fans, blowers, or exhaust systems to actively move air. It provides controlled, consistent airflow and predictable performance when properly set up. For hydrogen sulfide mitigation, mechanical ventilation is generally required whenever ventilation is used as a control. Hydrogen sulfide is heavier than air. It settles in low points and poorly ventilated areas. Effective ventilation must provide sufficient airflow volume, direct air movement through the entire work area, especially low points, operate continuously during the task, be verified through atmospheric monitoring. Ventilation effectiveness must always be verified through monitoring. Never assume ventilation is working based on fan operation or air movement alone. Monitoring confirms whether hydrogen sulfide concentrations are being reduced and maintained within safe limits. Ventilation intakes must be placed in clean air, free from hydrogen sulfide and other contaminants. If contaminated air is pulled into the space, ventilation can introduce new hazards instead of reducing the risk. Intake placement must avoid vehicle traffic and idling equipment, generators, compressors, or combustion engines, other work areas, or exhaust points. Exhaust from vehicles and equipment contains carbon monoxide, a colorless, odorless, and highly toxic gas. If ventilation intakes are near roadways, parking areas, or idling equipment, carbon monoxide can be drawn directly into the space, creating a situation where hydrogen sulfide levels are reduced, but you are exposed to carbon monoxide instead. Ducting must direct airflow through the work area and across your breathing zone. Reach low points where hydrogen sulfide accumulates. Avoid sharp bends and kinks that reduce airflow. Clean area flowing directly to the exhaust without sweeping the work area provides no protection. Ventilation must begin before work starts and continue through the work task. Remain in operation until work is complete and conditions are verified safe. Never be turned off to reduce noise, save power, or for convenience. Stopping ventilation or cycling it on and off can allow hydrogen sulfide to reaccumulate rapidly. Before entry, the space must be purged. Typically 5 to 7 complete air changes is used as a baseline. However, purge time is only a planning estimate. Entry is permitted only after atmospheric monitoring confirms hydrogen sulfide concentrations are reduced and stable within safe limits. Ventilation systems often appear to be working when they are not effectively controlling hydrogen sulfide hazards. Common failures include inadequate airflow, blower undersized for the space, long duct runs or multiple bends reduce effective airflow. Air movement is felt, but contaminants are not being removed. Short-circuiting. Clean air flows directly from the intake to the exhaust. Work area and low points remain contaminated. You see ventilation operating, but are still exposed. Contaminated intake air. Air pulled from areas containing hydrogen sulfide or other contaminants. Ventilation spreads contamination instead of removing it. Equipment failure. Mechanical failure of fans or blowers. Power interruptions. Collapsed, crushed, or leaking ducting. Obstructions inside the ductwork. Changing work conditions. Disturbing sludge or deposits release additional hydrogen sulfide. Opening systems or vessels during work. Process changes increase gas generation. Ventilation failure is often not immediately visible. The only reliable way to identify failure is through continuous atmospheric monitoring. Ventilation failure may be indicated by rising hydrogen sulfide readings, gas monitor alarms activating, loss of airflow or equipment failure, ducting collapses, kinks, or detaches from the blower. When ventilation fails, you must stop work immediately, exit the space or affected area, move to a designated safe location, notify your supervisor. Do not attempt to fix the problem while in the space. Reposition yourself to avoid the gas, or rely on PPE to continue the task. Failed ventilation means conditions are no longer controlled at the source. Work may only resume after ventilation is corrected, controls are reevaluated, and monitoring confirms conditions are stable and within safe limits. When setting up ventilation, be sure to verify the ventilation plan. Confirm that a ventilation procedure or plan exists for the work that you will be doing. It should include the required airflow rate, the duct placement, and the required purge time. If no plan exists or you're unsure, stop and ask a supervisor. Check the air intake location. You want to make sure that you're bringing clean air into the space. Construction sites can be full of sources of dirty air. Carbon monoxide exhaust from equipment and traffic is one of the most common pollutants in the airflow. Make sure the source of your airflow is free of potential contaminants. Check the blower and power supply. You want to make sure that the blower is large enough and has sufficient airflow. Verify that the blower has a stable power supply. And if it's hooked up to a generator, where is the exhaust from that generator going? Make sure that the power cord is appropriately placed so that nobody can accidentally trip over it and disconnect it. Inspect the entire ducting for damage, kinks, tears, holes, anything that could allow the airflow to go out of the ducting. If there is damage to the ducting, do not proceed. While purging the space, make sure you position the ducting to access the low spaces where hydrogen sulfide will be found. Ventilating the upper portions of the space is not going to be effective for hydrogen sulfide control. Short-circuiting occurs when the airflow enters and exits the space without reaching the hazard area. Make sure that the airflow reaches the space that you will be working. Verify adequate purge time. Allow the space to ventilate for the required purge time before you enter. This is typically between like 5 and 7 changes of air. Purge time should be indicated in your ventilation procedure. And remember, it's not enough to just purge the space. You must verify that that purge has been successful. Monitor atmospheric conditions. Use a gas detector to verify that the atmospheric conditions are safe. Be sure to check at the specific spot the employees will be working. Even with ventilation, we must verify that the hydrogen sulfide hazard has been managed. Do not assume that ventilation is working based on fan noise or air movement. Keep ventilation running continuously. Ensure that the blower remains powered and stays operating throughout the entire task. Do not turn off the blower to save power or reduce noise to try to communicate. If ventilation stops for any reason, just exit immediately. Do not enter until ventilation is restored and the atmosphere has been tested. Watch for changing conditions. Monitor your personal gas detector frequently during work. If levels start to rise, this is a sign that ventilation is becoming ineffective or conditions are changing. There are a lot of different ways that changing conditions can manifest itself. You might feel a change in temperature, you might feel a change in airflow, you might hear new sounds, you might feel something flowing through a pipe or a relief valve lifting. If there is some sort of change in conditions that you are not expecting, exit and reevaluate. Know the signs of a ventilation failure. You may feel a change in airflow, a change in temperature. Also, you may visually see that the blower ducting has become pinched or stepped on, or some sort of blockage has occurred. Some people like to tie a little string to something so they have a visual indicator of airflow. If ventilation fails, don't try to fix it, just exit. If for any reason ventilation cannot be set up properly, do not attempt to perform the work. Notify a supervisor and reevaluate the plan. In this section, we will examine why confined spaces significantly increase the hazard of hydrogen sulfide exposure. We will also learn how atmospheric contaminants behave differently in these spaces. Confined spaces are one of the most dangerous work environments that you will encounter. When hydrogen sulfide is present in a confined space, the risk can be extreme. The gas can accumulate quickly, reach deadly concentrations, and impede your ability to escape. A confined space is a space that meets all 3 of these criteria. It is large enough for you to enter and perform work. It has limited or restricted means for entry or exit. And it is not designed for continuous human occupancy. All 3 conditions must be present. If a space doesn't meet all 3 criteria, it is not a confined space under OSHA regulations. Examples include tanks, manholes, pits, vaults, vessels, trenches, sewers, and similar enclosed or partially enclosed spaces. A permit-required confined space is a confined space that contains one or more serious hazards, such as a hazardous atmosphere, including hydrogen sulfide, the potential for engulfment, internal configurations that could trap or asphyxiate you, and any other recognized serious safety or health hazard. Confined spaces increase hydrogen sulfide risk for several critical reasons. Limited air movement. Confined spaces restrict natural air circulation. In open areas, hydrogen sulfide may dilute or drift away. In confined spaces, gas can accumulate rapidly and reach dangerous concentrations with no warning. Restricted escape routes. If you had to climb down a ladder or crawl through an opening to get in, you'll have to do the same thing to get out, often while moving backward, in the dark, or while already experiencing the effects of hydrogen sulfide exposure. Confined spaces limit your ability to exit quickly when conditions deteriorate. Gas stratification. Hydrogen sulfide is heavier than air. In confined spaces, it doesn't mix evenly and sinks and forms layers. Instead of dispersing, hydrogen sulfide will sink to the lowest point, collect in pits, sumps, and depressions, and form invisible layers of contaminated air below cleaner air. This process is called gas stratification, and it creates a dangerous situation. The upper portion of the space may test safe, while the lower levels contain deadly concentrations. You may enter a space believing conditions are safe, only to encounter lethal hydrogen sulfide concentrations as you descend or move to lower areas. Because confined spaces restrict air movement and have limited volume, hydrogen sulfide concentrations can increase rapidly, sometimes within seconds. A space that has tested safe moments ago can become immediately dangerous to life and health if conditions change. If you encounter a permit-required confined space, stop. Do not enter. Notify your supervisor immediately. Your employer must determine what training and procedures are required. In this section, we will take a look at alternative entry procedures for permit-required confined spaces. We will discuss under what conditions alternative entry is allowed. Alternative entry is a specific, narrowly defined procedure for entering confined spaces allowed by OSHA. It is for certain permit-required confined spaces where the atmospheric hazard is the only hazard of the space, and that hazard can be eliminated through ventilation. It is not an automatic shortcut, and it does not eliminate the need for procedures and controls. Alternative entry is a method for entering certain permit-required confined spaces without using the full permit system, but only when both of these conditions are met. Atmospheric hazards are the only hazard present, and those hazards can be fully controlled by continuous forced air ventilation. Alternative entry does not remove the employer's responsibility to evaluate hazards, establish written procedures, or ensure your safety. It is a limited exception to a full permit-required entry, not a different type of space. OSHA allows alternative entry to provide flexibility when hazards are well understood and limited to atmospheric conditions only, continuous forced air ventilation can reliably maintain safe air quality throughout the work, atmospheric monitoring can verify that conditions remain safe. When ventilation and monitoring can continuously control atmospheric hazards, the full permit system, with attendants, rescue plans, and entry supervisors, may not be necessary. However, if ventilation cannot maintain safe conditions, or if any non-atmospheric hazard exists, alternative entry is not allowed. Before alternative entry can be used, your employer must evaluate the space and confirm that only atmospheric hazards are present. Establish written alternative entry procedures specific to the space and task. Provide and maintain continuous forced air ventilation capable of controlling the hazard. Provide calibrated atmospheric monitoring equipment, personal monitors, and if needed, testing equipment. Complete and sign a written certification confirming the space is safe for alternative entry. Make the certification available to you or your authorized representative. Train on the alternative entry procedures for that specific space. Alternative entry is employer controlled. You should never assume alternative entry is allowed based on past work, informal approval, or your own assessment. If your employer authorizes alternative entry, you should verify that a written certification exists. It must be signed, dated, and verified that the atmospheric hazard is the only hazard of the space. Verify that the ventilation is operating. Confirm that the blower is running and producing airflow. Check that the ducting is properly positioned, and verify a reliable power supply. Verify that your personal gas monitor is functioning. Calibration must be verified and it must have been bump tested. Confirm that the required atmospheric testing has been completed. You need to check for appropriate levels of oxygen, flammable gases, and toxic gases. During entry, keep the ventilation running continuously. Monitor the atmospheric conditions. Keep an eye on your gas monitor, and if levels start to rise, that is a sign of changing conditions. If an alarm sounds, exit immediately. If there is an unexpected change in conditions, exit and reevaluate. Work in confined spaces can be very dangerous. It's important to understand that alternative entry is still a type of confined space entry. It requires extensive planning and training on permit-required confined spaces. In this section, we will discuss respirators as a backup method for managing hydrogen sulfide hazards. Respiratory protection is not a primary means for protecting employees from hydrogen sulfide. Respiratory protection for hydrogen sulfide is typically only used if primary methods fail or other protective methods are infeasible. Respirators may only be worn when authorized by the employer and as part of a written company respiratory protection program. If respiratory protection is required for routine work, this is a sign that engineering controls are inadequate. Respiratory protection is the last line of defense in the hierarchy of controls. OSHA's Air Contaminant Standards 29 CFR 1910.1000E allows respirator use only when engineering and administrative controls are not feasible or do not adequately control the exposure. This means respirators should not replace ventilation or other engineering controls. If respirators become necessary for routine work, the underlying controls have failed or are inadequate. Relying on respirators to perform tasks that could be controlled at the source is not an acceptable practice. The presence of a respirator requirement for routine work could indicate a hazard that is inadequately controlled. Respiratory protection may be required in specific limited situations. Unexpected hydrogen sulfide releases, engineering control failures such as ventilation stops and equipment breakdown, or emergency response or rescue operations. Non-routine work, short duration tasks where engineering controls cannot be implemented. Emergency repairs where controls cannot be established first. Situations where implementing engineering controls would create greater hazards. If you are being asked to wear a respirator for what appears to be routine work, stop and ask your supervisor, why is respiratory protection needed for this task? What changed that made existing controls inadequate? Has the hazard been reevaluated? Should work be stopped until better controls are in place? Air purifying respirators do not supply oxygen. They only filter or absorb contaminants from surrounding air. Air purifying respirators only work in atmospheres with adequate oxygen, at least 19.5%. Air purifying respirators are limited to specific maximum concentrations based on their assigned protection factors and manufacturer approval. For hydrogen sulfide, air purifying respirator use is limited and not appropriate for unknown, uncontrolled, or potentially high concentration conditions. Cartridge service life is limited and difficult to predict. Cartridges can be exhausted without warning. Air purifying respirators require proper fit to provide protection. Because hydrogen sulfide can reach dangerous levels rapidly and cartridge life is unpredictable, air purifying respirators are not reliable protection for uncontrolled, unknown, or high concentration conditions. In immediately dangerous to life and health or unknown atmospheres, such as hydrogen sulfide concentrations at or near 100 parts per million, or when levels cannot be determined, only air-supplying respirators provide appropriate protection. This includes self-contained breathing apparatus, SCBA, or supplied air respirators. If hydrogen sulfide concentrations cannot be determined through monitoring, conditions must be assumed to be immediately dangerous to life and health until proven otherwise through atmospheric testing. Entry into IDLH atmospheres requires specialized training. Such entry is typically governed by 29 CFR 1910-146 permit-required confined spaces, and, when emergency response or rescue operations are involved, may also require training under 29 CFR 1910.120 hazardous waste operations and emergency response. Emergency escape respirators are designed only to allow safe evacuation, not to perform work. They are not approved for entry or work in contaminated atmospheres. They provide very limited protection, typically 5 to 15 minutes, and are intended solely to help you reach fresh air during an emergency evacuation. Emergency escape respirators and evacuation procedures will be covered in detail in separate hydrogen sulfide emergency response training. When respirators are used in the workplace, OSHA requires the employer to implement a written respiratory protection program in accordance with 29 CFR 1910.134. This program must include atmospheric testing to identify hazards, medical evaluations to ensure workers are physically able to wear respirators, proper respirator selection based on the hazard, fit testing for tight-fitting respirators, training on respirator use, limitations, and maintenance, procedures for cleaning, storing, inspecting, and maintaining respirators, and program evaluation and oversight. Respirator use must be planned, evaluated, and managed by the employer. If you are required to wear a respirator, you must receive specialized respiratory protection training in accordance with 29 CFR 1910.134 before use. If you are asked to wear a respirator for hydrogen sulfide as part of routine work, you should consider that a warning sign. Ask yourself and your supervisor, have engineering controls failed or are they not available? Is the ventilation inadequate? Maybe the hazard is greater than expected. Should we stop this work until controls can be improved? You have the right to ask why respiratory protection is necessary. You can request to see the atmospheric monitoring results. Review the controls that are in place. You have the right to stop work if there is any indication that safety is being compromised. Now, your employer may have perfectly legitimate reasons for requiring respiratory protection. It can sometimes be used for emergency repairs or short-duration tasks for which ventilation or other controls can be implemented. However, routine use of respirators for hydrogen sulfide can signal inadequate hazard controls. In this course, we have learned how hydrogen sulfide hazards are controlled through engineering and administrative controls, continuous monitoring, and proper procedures. Here's the thing that I really want you to remember. When alarms activate, conditions change, or controls fail, exit immediately. Hydrogen sulfide can incapacitate within seconds. There is no time to investigate. There is no time to fix the problem, and there is no time to second-guess yourself. A hydrogen sulfide alarm is not a suggestion. It is a command. You can stop work when gas monitor alarms activate, ventilation fails, atmospheric readings are rising, or you have any indication that work conditions may be unsafe. In my years with working with hydrogen sulfide hazards in the Navy, I have learned a critical lesson. The workers who go home safely are the ones who treat every alarm, every changing condition, and every control failure as a signal as to what it is, a sign to leave. Hesitation can cost you your life. Don't let that be you.